Hello everyone and welcome to this Neptune CFD boiling tutorial. In this tutorial we are going to simulate a two-phase boiling flow inside a rectangular channel. There will be three cases in this tutorial in order to present the influence of a few parameters on boiling flow simulation results. So the first case is a standard boiling flow with a constant bubbles diameter. So first of all you need to create a study called boiling with a case. Then you can go on the boiling directory and copy from the Neptune CFD installation directory the mesh M1 into your mesh directory. Then go on your case directory, data, and launch the shell script Neptune CFD. Once the graphical user interface is opened, go on the mesh and add the M1 mesh. Then on boundary zones, add 6 boundary zones. So there will be 2 symmetries, 1 inlet, 1 outlet, and 2 walls. Then add the selection criteria corresponding to the boundary region. Then on calculation features, check Eolian multiphase and choose the bubbly flow option. Then click on yes and activate heat and mass transfer. On main fields, you just need to change the labels for the water and for the steam. Here the energy resolution is checked. Then click on turbulence models. For the water we are gonna set a K epsilon turbulence model, and for the steam known. And for the reverse coupling choose large inclusions for the steam. Then add the gravity on the Y component on body forces. Then click on closure modeling. For the water-steam interaction, all the parameters are already set. Then go on interfacial area. For this case, we're gonna set a constant model for the steam with a default diameter of 1 mm. Then click on interfacial enthalpy transfer. All the parameters are set automatically. And same for the wall transfer parameters. Then on volume conditions, check initialization. Then click on all cells. For the thermodynamics properties, the Cathar method is used. Then go on the initialization tab. For the pressure, set an initial pressure of 150 bars. For the water field, initially there's no velocity and all the domain is filled with water, so set a fraction of 1. And for the temperature, set a value of 610 kelvins. And for the steam field, initially there's no steam, so put a velocity of 0, a fraction of 0. And for the thermal properties, set saturation enthalpy. Now you need to change the nature of the different boundary zone. Once it's done, click on the inlet condition. For the water field, set fraction of 1. And for the velocity, we're gonna choose mass flow rate and set a value of 0.02 kg per second. And for the thermal field, set a temperature of 610 kelvins. No steam will arrive from the inlet, so you can let the default settings with a fraction of 0. Now for the outlet, set a reference pressure of 150 bars and set a fraction of 1 for the water field. And for the steam field, set a value of 0 for the fraction. For the wall 1, set a 0 flux. And for the wall 2, we're going to set a flux with the following value. Then go on time settings and choose an adaptive time step with a time analysis of 2 seconds. Then you can go on post-processing. In the writer tab, set an output every 10 time steps. Then we're going to add some monitoring points. Then go on profiles and add a profile along the heated wall. So S is a value which will vary from 0 to 1. And for these colors, we're going to set the water temperature and the volumic fraction of steam. Then save your simulation and run the calculation. Once it's done, you can click on Convergence tool. We can plot some variables against the simulation time at monitoring points location. Then go back on your terminal window in the residue directory. Go on the profiles directory. You can edit the file and delete the first lines. Then you can create a Python script as follows. So it will plot the steam fraction against the time. So we can see the evolution of the steam volume fraction along the heated wall. Then we can post-process the results using ParaView. We can display the volumic fraction of water. You can change the scale in the Y direction. Then we can display the water temperature. Now we're going to create a second case called AI. So this is a standard boiling with interfacial area transport. So go back in your study directory, boiling, and launch the following command: netUnCFD create, copy from the previous case and the new case name AI. So all the setup and all the files from the previous case will automatically be set in the new case. So you need to go in interfacial area and change the model to interfacial area transport with the following default diameter. Then for the inlet condition, in the steam field, you need to change the interfacial area to the diameter you just set. And in profiles, you can withdraw the two variables and add the steam diameter. Then add another profile called outlet prof. The profile will be set alongside the outlet on the top of the domain. Then on volume solution control, you need to add the post-processing of the steam diameter. so you can post-process the results in ParaView. Then save your simulation and run the calculation. With the same Python script as before, we can display the steam bubbles diameter along the heated wall. And same thing for the steam bubbles diameter along the outlet. And then you can open ParaView to post-process the results. We can display the steam diameter. Now for the third case, it's going to be a boiling flow with interfacial area transport and bubbles injection. So you need to create a new case with the option copy from. So you're going to create the 3PHI case based on the AI case. So go in your case directory, data, and launch the shell script engine CFD to open the graphical user interface. On calculation features, we're going to change the option to user defined and click on yes. So it's going to reset the different parameters you set earlier. So on main fields, change the field label for the water and for the steam, and add a new field called air. Change the phase to gas, and set dispersed for the steam and for the air. On turbulence models, set the same parameters as from the previous case, and set large inclusions also for the air. So here the body force is kept from the previous case, so click on closure modeling. For the water-steam interaction, change the turbulent dispersion to GTD model, and for the wall forces, set none. Then for the water-air interaction, set the turbulent dispersion to GTD model. Then on interfacial area, for the steam field, set the model to interfacial area transport with the following default diameter. And for the air field, choose a constant model with a default diameter of 3 mm. So no need to change anything in the interfacial enthalpy transfer. And then click on wall transfer parameters and change the wall transfer model to y plus. So the fluid properties will be at y plus equal 250. And then click on all cells. For the air field, change the method to user properties. For the air temperature, change the expression as follows. So the temperature is based on the air enthalpy. Then change the expression for the density based on gamma, the pressure, and the air enthalpy. Then set the different values for the viscosity, the specific heat, and the thermal conductivity. You can then click on the initialization tab. You can check if everything you set earlier is well defined. So for the water, yes. For the steam, set saturation enthalpy. Then for the air, initially there's no velocity, there's no air, so put a fraction of 0. And for the thermal field, choose enthalpy and set the following value. Now for the boundary conditions, click on Inlet. For the water field, change the fraction to 0.9. For the mass flow rate, choose a value of 0.011 kg per second. Let the other values as it is. For the steam field, no need to change anything. And for the air field, choose a fraction of 0.1 and a velocity of 5 meters per second. Then for the thermal field, choose imposed enthalpy with the following value. Then click on Outlet. You don't need to change anything for the three fields. And same for the two walls, no need to change anything. For the time settings, the properties remain unchanged. Then click on the numerical parameters. Let the velocity predictor algorithm as coupled. Then click on volume solution control and check the air diameter for the post-processing. So you can post-process it using ParaView. Finally, click on Profiles. You can delete the outlet profile. And for the wall profile, add the air temperature for the variable. Then save your simulation and go back in your terminal window. Go in your source directory and copy from the Neptune CFD installation directory the source inc user it thermal.c. For this case, this subroutine will be used to calculate the coefficient of the interfacial energy transfer between the air field and the water field. Then go back in your data directory and launch the graphical user interface. And you can now launch the calculation. Once it's done, we can post-process the results using ParaView. We can display the air temperature and see its evolution. Same thing for the volumic fraction of water. Then, using the same Python script as before, we can plot the air temperature along the heated wall